All right, well, we're going to continue chapter 29 here, and we're looking at magnetic force, and this time acting on a wire. Okay, so that's what we're looking at today. Very similar actually to what we saw last time with charges, moving charges. So the equation we saw last time for a charge, let me write it up here. I'll do it like in blue. So magnetic force QV cross product V. Okay, so we have the cross product here, and that cross product, knowing the direction of V and B, we use the right-hand rule, and using the right-hand rule, we could find the direction of magnetic force. So we looked at a couple of examples last time. I think the last example we looked at was a velocity selector, and how we could determine the direction and magnitude of the magnetic field using this. Okay, so we're gonna replace this though. We want to eventually talk about a current, right? So if I have like a wire here, right, some current like this, and it's in a magnetic field. So let me draw my magnetic field in green here. So let's say I have a magnetic field going into the page. Okay, so my question is, how is what we talk about here, right, with a moving charge, how is that related to this? Okay, there's a couple of ways I can answer that question. One, if you think about current, current is just a flow of positive charge, and we know that this is we're actually looking at as the electrons are moving in the opposite direction. Since VV. Okay, so if these electrons are moving to the left here, inside a magnetic field, right, they're going to feel a force. Right? And let's try to figure out what direction that force is. So I said last class that when you have an electron, you have to remember to use the left-hand rule, or the other option is to use a right-hand rule and flip your answer at the end. All right, but I like just using the left-hand rule. So for negative charges, we use the left-hand rule, and try using it here. Okay, so remember your thumb represents velocity, pointer represents magnetic field, and your middle finger represents force. So remember, we should have something like this, right? So your thumb represents velocity. I'm using my left hand, by the way. Thumb represents velocity, pointer or your index finger represents magnetic field, and your middle finger, which is always pointing out parallel to your palm, right, coming out of your palm here, is your force. Okay, so line those three fingers up, and we'll line it up. So yeah, quick question here: shouldn't electrons move in the direction of current? Well, remember we said when we're talking about current is actually defined as a flow of positive charges, even though that's not what's actually going on. So this whole time, we're looking at circuits, and we're talking about the current. That's a flow of positive charges. Electrons, what actually is going on, goes the opposite direction. Okay, so this is because we defined current before we actually understood electrons. But then after looking at electrons, actually electrons go the opposite direction. But industry had already been, I want to say normalized, or I don't know, what's the word, standardized for that direction. Anyway. All right, so what direction you guys get using the, in this case, using the left-hand rule here? What's the direction of your force? Okay, what does a pointer and middle finger represent again? Okay, so the pointer represents your magnetic field. So that's in this case, it's green, right? So green is going into your screen. So your pointer should be pointing into your screen here. And the middle finger represents force. And that's what we're trying to find. So for this question, what direction is your middle finger pointing after you set this up? Yeah, it is upward. So if we're using the left-hand rule, don't use the right hand. If you're using the right hand, you got to flip your answer at the end. Okay, so I guess you could still use the right hand, but you got to remember to flip it. I'm using the left hand roll. So if I use the left hand roll, velocity is going to the left, right? So here's my velocity going to the left. That's my velocity. The magnetic field is going into the screen. Again, so I'm adjusting myself for your perspective. I'm gonna make my middle finger go into the screen here. And you can see my middle finger points up, okay? So you guys should be seeing something really similar. Your pointer should be pointing into the screen here. And you have your middle finger going up, okay? All right, so what that tells us is that force is going upwards, acting on these charges as they move. Okay, now how can I relate this to currents? Well, let's think about QV. Okay, so is it flipped because it's a negative charge? So if you're using the right hand rule, not left hand, if you're using your right hand for this, yeah, you should get your force pointing down, and you're exactly right. Because it's a negative charge, we have to flip what the right hand gives us. Okay. That's why I said alternatively, what you could, instead of doing the right hand, you could do the left hand, and the left hand, because it's the opposite of your right hand, it already flips the sign. So you don't have to do any extra flipping using the negative hand. Okay, so I hope that makes sense. I hope I'm not confusing you. Yeah, good. All right, so QV. Let's look at QV. QV, if I want to change this to, I can't remember if we did this already. Well, I'm gonna make a couple of substitutions here. For Q, I know Q is related to the current, right? So current equals your delta Q over delta T. Or let's just put delta T here for now. Okay, so that Q, I could substitute, instead of Q, put current times time. All right, and velocity, well, velocity is just the distance, in this case, the length of the wire over time. So this equals current times L. So if I want to rewrite this equation here for the force on a wire, it's really similar. It becomes I L cross product B, and we recognize that when we're talking about this over here, this velocity, this velocity here, that velocity has a direction, right? So we need to have a direction over here. My bad, I should have put a direction here. So magnetic field has a direction, and what has the direction is L. Okay, L will be the same direction as your currents. Okay, so that gives us kind of a different way of looking at this wire down here. So if I'm looking at this wire down here, instead of thinking about what the charge is doing, or in this case, charge is going to the left, let's just look at the currents. Current is going to the right, magnetic field is going in. Okay, that means, according to this equation, my first vector, right, that's my thumb. My thumb should be along the direction of current, so your thumb should be pointing to the right, and magnetic field is your index finger, right? And your index finger should be pointing inwards for this one. You should get the same force. Okay, so let me repeat that in case you didn't catch it. I know I did it kind of fast. Okay, so the direction of current, that's going to be given by your thumb here. So you put your thumb in the direction of current. Oops. Okay, and then for a magnetic field, that's going to be, you're going to put your index finger right in that direction. Okay, and you are going to be using your right hand. Okay, because we're not looking at negative charges, right? Current is a flow of positive charges. So we're looking at using our right-hand rule for this. So if you line up those things, your thumb is your current, your index finger represents your magnetic field. You should get the force going in the same direction. Okay. You guys see that? All right. So that's a right-hand rule for wires. Not a whole lot different. You still have the cross products, so the same same idea as the charge. Okay, the same properties we talked about last time, where if the current has to be making some angle with the magnetic field, and the force is always going to be perpendicular to your current. Okay, so I'm going to zoom in here. I'm going to zoom into this wire and see what's happening to these charges, and it's something that that is not intuitive when we first look at it. So we're going to zoom in and look at a small segment of wire. Oops. Okay, so I'm going to draw my wire here. So I'm going to draw my wire pretty big because, again, we're zooming in, right? To black here. Okay, here's my segment of wire. And let's say I have current. Let's say current's going in the same direction. So if my current was going to the right, current's going on, that means I have a whole bunch of electrons, right, moving to the left. Okay, so I have all these electrons moving this way. Okay, and then let's say I have a magnetic field. My magnetic field is going into the page here. Okay. Now we already talked about this, right? Using the right-hand rule, we saw that these electrons are going to be going up. Okay, so I'm a little confused on how we get the direction of magnetic field. Okay, so the magnetic field is an external magnetic field. Okay, it was given to us in the problem that we have this magnetic field going into the page. Okay, maybe I should have mentioned that earlier. So don't get that confused with the magnetic field due to the wire. Okay, so we talked about that earlier, that a magnetic field does create its, a wire does create its own magnetic field when you have current through it. What I'm drawing here is not the magnetic field due to the wire. It's an external magnetic field. It's a magnetic field from some magnet that has been set up, okay? I hope that makes sense. We're not, yeah, outside source, that's right. Okay, so it's given to us in the problem. We don't have to figure out the direction. All right, so we looked at this earlier and we saw that we're gonna get a force going, let's see, am I doing this right? Did we got a force going upward, right? This is the same picture as last time? Yeah. Electrons going to the left. Magnetic field going in. So we got a force going up. You know, something strange is happening here. Okay, I guess I just drew it wrong in my notes. All right, so we'll stick with what I have here. So what's going to happen as you start to have flow, these electrons start to flow. Eventually, we start to get electrons accumulating at the top, right? So these electrons are going to start to move upwards, right? Because there's a force acting on it. So they're going to start to move up like this, and we're going to have all these negatives here at the top of the wire. Okay, and if we have all the negatives on the top of the wire, on the bottom of the wire, then that means we have positives. We start to have that separation of charge here. Let me erase these electrons really quick, the ones in the middle, because we know what's happening to them. Okay, so let me just erase these here. Okay, so we start to have these, the separation of charge, and if we have a separation of charge here, that means we're going to have an electric field being created inside the wire. Let's see, I'll do electric field. I guess in this lighter blue would be good. Okay, so my electric field will look something like this. Okay, now, so we have electric field going down, and the more charge that accumulates in here, the more electric field we're going to have. Okay, so what we start to see here is a buildup of charge. That buildup of charge then creates an a voltage, right? So buildup of charge, this buildup of charge begins to create electric field. Which gives us a voltage. Okay, so there's a voltage. Remember, electric field always goes from higher voltage to lower voltage, right? So now we have a voltage difference in the wire. I'll call this delta V here. Okay, there's a change in voltage there. Okay, so what's going to happen? The more charge, as more charge starts to flow through that wire, I am going to start getting more charge build up on the top. Eventually, though, let me put in another electron here. Let's say there has been building up for a little while, and now I have this another electron's coming in. Certain speed v. Guys, I did something wrong here. Really kind of rookie mistake. Yes, thank you. Don't be afraid to call me out on that. Okay, so it's like, yeah, don't go for it. Go for it. If you want to call me out, go for it. All right, yeah, that's like a rookie mistake, or I could put like physics 221 noob mistake. Maybe you could put it that way. All right. Anyway, so electric field comes out of the positive, goes towards the negative. Okay. Oh yeah. All right. So let's go back to this electron. So this electron is going to the left now, and as this electron is moving to the left, well, first it's still in the magnetic field, right? So we know there's going to be an upward force acting on that magnetic field, acting on that charge from the magnetic field. I'll call that FB here. Okay, but now since it's in the electric field, that electric field gives it a force downward as well, or give it a downward force. So eventually, there's going to be so much buildup in charge that the electric field is going to be strong enough to counter this magnetic force. Okay, so that electric force is going to eventually counter the magnetic force. Okay, that's when it kind of reaches maximum voltage. All right, so let me go off to the side here. Yeah, it's going to be equal and opposite, exactly. So at the point when it's equal opposite, I could say FE equals FB. And we kind of already did this earlier. But I'm going to take a slightly different approach. We know we're looking at electrons, right? So FE is just QE, and FB is QVB, where V is the velocity of the electron. Okay, we actually did something really similar with a selector. Now, here's where we're going to deviate from what I did with the velocity selector. Electric field, well, that's related to voltage, right? If we have a constant electric field, I could say electric field equals my delta V, change in voltage, over that distance of the wire, right? And that distance will be the diameter of the wire. So I'm going to put that as D. Okay. So I'll make that substitution here. The voltage difference from the top of the wire to the bottom of the wire, delta V over D, equals Q VB here. And I'm going to solve for delta H here. Or sorry, not delta H, delta V. So if I solve for delta V, the voltage across this wire is going to, the Q's cancel out, so charge goes away. And what is that, dVB? So the diameter of the wire times the velocity, which is a drift velocity. I'll put VD here. This is our drift velocity of the electron. We talked about that in chapter 27. And then times magnetic field. Okay, so this is a voltage, not the typical voltage we talk about. Right? When we talk about voltage in wires, usually from this side to this side, right? As the current, as the electrons go this way, right? It's going to higher voltage. That's not the voltage we're talking about. The voltage we're looking at is this voltage right here, in between the thickness of the wire. Okay, and that has a special name. That's called the Hall voltage. All right. So really, kind of important voltage here, especially with electronics. I was telling you guys earlier that I was looking up how to do your lab, and it turns out that the magnetometers, the magnetic meters in your phone, uses this idea of Hall voltage to measure magnetic field, and it kind of makes sense because this delta V here is going to be a really small number. Think about what like the values that we're plugging in here. The diameter for a wire. Okay, so if we're talking about a wire here, even for like a thick wire, this is like in the order of millimeters here. Drift velocity. We saw drift velocity is in the earlier chapters is 10 to the -4 meters per second. And magnetic fields. Well, these magnetic fields are usually in the order of microteslas. So all these values are pretty small, which means you get a pretty small voltage here for delta V. Okay, and so if you have a very sensitive electronics that can measure small changes in voltage, then that's how we're able to measure magnetic fields in our phones, by measuring this delta V here. Okay, so kind of interesting there, kind of interesting application of this I don't know what to call it, magnetic force here. Okay. All right. Could go a little bit further into this derivation, kind of going back into what drift velocity depends on, but we're gonna stop there. As your book goes a little bit more into this, it's just more substitutions. But I'm gonna stop here for my derivation. Okay. Let me know if you guys have questions. I'll gladly go back. So let's look at, now zooming out, going into a regular wire. I'm going to look at a wire that has a different shape, and I want to know what is the force on it. So I have this example here where I have this wire, looks like this. Oh, whoops. Semicircular there, and this has a radius r. Okay, and then we have magnetic field. One more thing here. Current is going this way. Okay, so that's my current. Okay, so in this problem, I'm gonna have a magnetic field coming out of the page everywhere. So it's out of the screen here, coming out towards you. Okay. So here's my next, I forgot to write the problem. So here's my next example that we're going to do. And let's see, I can put it right here. What is net force acting on the oops. Okay, so we're trying to find the net force acting on the semicircular part of the wire. The knots, the flat parts are pretty easy. So this part right here and this part right here, straight wires are, you know, a simple right-hand rule, right? You put your thumb in the direction of current, index finger goes the direction of magnetic field, and what you should see for this one and this one is that you get a force going upwards. So this provides a force going upwards. Okay, right, double check me with the right-hand rule. Thumb is your current, pointer is your magnetic field, which the magnetic field is coming out towards you guys. The force is, your middle finger is force. All right, so yeah. All right, so if we look at the wire now, the wire, the semicircular wire, if you do it at different segments here, so just you do the right-hand rule for, let me bring up my highlighter. Do it for different segments. Let's do it for this segment here, and this segment here. Okay, I want you to do the right-hand rule for those different segments. You know, if you do the right-hand rule for those, what do you get? Well, you should get that the force is always going to be coming out like this. Now, let me erase that because I'm going to run out of space here. And I'll call this DF because this is a force acting on a small segment of wire. All right, so just by using right-hand rule those different segments, you should be getting the current kind of pointing outward there. Okay, remember the magnetic field is coming out towards you. All right, so anyone see that? Those different forces? We are applying the right-hand rule here. So let's look at, let me look at one of them. Let's look at this one right here, because you're going to do the same process for the rest of it. Okay, so first of all, remember what the cross product does. The cross product gives you a vector that is perpendicular, right, to your other vectors. Cross products always do that. They always give you perpendicular. Okay. Okay, so right here, current is going down, right, kind of downward at an angle. Okay, so I want you to put your thumb kind of down at this angle. So I'll try to do it with you guys, even though. So we have current kind of going down like this, right, going downwards, kind of down to the left, right? So I want to put my thumb in that direction. Okay, my pointer here, well, my pointer is going out of the screen. So I'm going to point my pointer out towards you guys, like that, right? It's coming out of the screen. And then my middle finger, which extends perpendicular to both of those, you see it's going upwards, right? So if I line up my, I'm kind of twisting my arm here. All right, so my thumb's going down to the right. My pointer finger is coming out of the screen towards you, and you can see my middle finger is kind of going up and to the up and to the left, right? So perpendicular to the current there. Okay, so I know not the best way of seeing it, but hopefully you can see what my fingers are doing there. Twisting my wrist there. All right, so a little tricky when you have those angles, but remember that your force is, when you do the cross product, is always going to be perpendicular to your currents. Okay, always be perpendicular to your currents. Yeah, I mean, it's kind of it kind of goes in the direction of the normal direction. Yeah, I don't mind explaining it again. Okay, so take your so here's where you hear the right hand rule, right? Always keep your fingers kind of like this. They're all somewhat perpendicular to each other as best you can. Okay, so we're gonna take our hand, right hand rule, put our thumb in the direction of currents. Current is going. Let me draw it here so we can see it a little bit clearer. Current is going down at that moment, right at that point of the wire. Current is going down and to the left there. Okay, so I'm gonna take my hand, take my thumb, point my thumb down and to the left. Okay, so I'm gonna go. I stand like this. Okay, so my thumb is gonna go down, or to the left and down. Okay, so that I'm just focusing on my thumb right now. Right, it should match the direction of your current. Right, going down and to the left. Okay, then your magnetic field, right, your pointer needs to go out of the screen, right, coming towards you. Okay, so make your pointer, your index finger point towards you. Okay, so I'm gonna make my index finger point towards you. Okay, and keep your thumb. I'm trying to do this without breaking my wrist. Keep your thumb going down to the left. Okay. Okay, so again, I'm altering my the way I'm doing my hand for your perspective. Okay, so it should be matched. We should be having the same, really similar things. Okay, so your thumb going down to the left, index finger coming out towards you, pointing out towards you, and then your middle finger sticking straight up. All right, and you can see the direction of that middle finger, kind of going upwards and to the right. Okay. Well, all right. So I think that's the last time I'm doing that. Okay. So, all right. So that's what the right hand rule gives us. We could see, no problem. You can see how the forces on every segment of wire changes a little bit, where it changes direction, but it's always perpendicular. Okay. So if we're looking at this, okay, why is a pointer finger pointing at us? Because the magnetic field is coming out towards you. So these dots right here represent the magnetic field, and when it's a dot, that means magnetic field is coming out of the screen, right towards you. Yeah, the direction of the magnetic field would be given in a problem. Otherwise, you couldn't find force. So yeah, the direction of the magnetic field would be given, or enough information will be given so you could find magnetic field. So if, for example, what if current and force were given, you can use current and force to find the direction of magnetic field. But in this problem, it's a given, yeah. All right. So how do we go from this? So we could, if we look at our forces here, and we're gonna add up all the forces on this arc, what do you expect to happen to the components? You see it there? If you add up, so adding up all the components, which is what we're going to do in a second. Yeah, that's right. Yeah, X components cancel. Leaving just the Y components. So we get an overall upward force is what we expect. Okay. Yeah, net upward force is what we expect. All right, so that's what symmetry tells us. Let's see if we can get that using by derivation, by just the math. Okay, so in order to do that, I'm gonna just blow up a section of this. I'm gonna look at this section here. I'm just gonna look at that section. So blowing up that section, I'm gonna redraw that down at the bottom. Okay. And let's look at a small segment of wire, right? So a small segment of wire, will be let's say, look at this segment right here. So in that segment, we have a current, right? That current is going in this direction. I'm going to call this DL. Okay, because well, remember what we talked about L. L goes in the direction of current, but it's also length. And that length is a small segment of that length. So I'm going to call it, I'm just going to call it DL, right? Because it's a segment, it's not the whole length. And I'm going to have to draw an axis here. So let me draw my axis like this. Oopsie. Okay, this is my x-axis. I don't think I drew too close to the edge there. Y-axis. Okay, and here's the location of my DL, right? DL is like this, as distance r, at some angle theta. Okay, so I'm gonna do a couple of things with this DL. This DL, let me before I get there, we're trying to find force, right? So I need to find the force for this segment of wire first. For this segment of wire DF, we're just going to use our equation that we got last time. I dl cross product B. Okay, that's my equation for a force on a wire. And I'm just, the DF and the DL just means that we're looking at a small segment of wire, giving us a small amount of force, right? The DF. Okay. So what I want to do in order to use that equation, I need to get an equation, or I need to get an expression for DL in terms of direction here. This DL I could express in terms of components. DL, so the magnitude DL, whatever that length is, times, and there's my theta there. If I want the x component, it would be negative sine theta to give me the x component of that vector. And then the y component, DL, y component would be cosine theta. Just be careful with that angle. That cosine theta is a horizontal in that picture. This theta here, let me explain that really quick. This theta here, because this is 90, is related to the vertical, the angle between the vertical here. So that's why I'm using sine theta for the x, cosine theta for the y, because I could draw it out. I anticipate you guys having that question. If I draw this out really quick, where's that theta? Let me do it in red. So here's my x-axis, here's my y-axis. Where's that theta? That theta shows up right here. So it's relative to the vertical. Okay. All right. Maybe you didn't have that question, but that's the answer. And that'll be J hat here. Okay. All right, and then I'm going to do one more substitution here. You know what? Let me answer your question. So is the current a scalar? Yes, I is a scalar. We give the direction of the current with L. So L is kind of more like a position vector, but it goes in the same direction as your current. So yeah, it's hard to go from QV, where V is clearly a vector, right? Velocity is a vector, to IL. And so we just kind of sneak the vector with a DL. Okay, I'm gonna make one more substitution here. What is DL? Well, we're looking at an arc, right? DL is just arc length, so it's RD theta here for DL. And then of course you have all this stuff, sine theta I hat plus cosine theta j hat. Okay, so that's my DL. So let me take my DL and plug it in to my equation up here. So I R d theta, and then you have your negative sine theta I hat plus cosine theta j hat. Oops. Cross product there with the magnetic field. So magnetic field, I'm just going to put B k hat, right? It's coming out of the page. And so that would be in the, k hat direction. Okay, so we're going to have to do a, we're going to have to distribute here. I'm going to distribute, because this is a cross product, right? So I'm going to distribute this B k hat to this first term, and this B k hat to the second term. Oh, you know what I could also do? I could just take out all the constants. I, R, B, all these three are constants here. So let me just do that. Let me take out the constants. So I, R, B, and then what I have is this negative sine theta, d theta, and the cross product of I hat cross k hat. Where that cross product come from? It came from the fact that I distributed. I distributed my k hat here to both terms. So I hat, so that's where the I hat cross k hat, and then I'm going to distribute this k hat to the j hat. So my next term would be plus cosine theta d theta, and this would be j hat cross k hat. Okay, so I'm just doing algebra there. You're distributing things and all that. And this is, of course, my df. Okay. So we're going to do the right-hand rule for the I hat cross j hat stuff. So I hat cross j hat, if you do that right-hand rule for those vectors, put your thumb in the x direction, put your pointer finger in the positive z direction. What you get when you do this I hat cross k hat is a negative j hat. Okay, and then you could do something similar over here with the j hat cross k hat. Put your thumb in the j, put your index finger in the positive z, and what you get is a positive I hat here. Yeah, do it a little bit better. So talk about what we talked in the beginning of this problem when we looked at this. We said that we should not have an x component, right? They should cancel out. So I'm hoping that when we do this integral, we're gonna, it's this d theta there. When we do the integral, we should see the I hat going away. Yeah, and there's definitely some similarities to torque, right? Because torque in your 3A class use cross products, right? That's how you define torque. So yeah, a lot of crossover there. Okay, so let's integrate. I'm going to integrate both sides here. Now on the left side we just get F, right? So we just get our total force, which is what we want. On the right side, well, IRB are constants, so I'm going to take out IRB. We don't need to have those in the integral. And integral sine theta d theta j hat. All right, those two negatives there, this negative and this negative cancel out, so they go away. I put a bracket here. And what do we mean by limits? Well, to determine the limits, we got to see how we define theta in the first place. This is how I define theta. So the smallest theta we have is when we're looking down here, right? At this point. So that'll be a theta of 0. The largest theta we have, well, it goes beyond, outside my picture that I drew. The largest theta we have, it goes when you go all the way over here to the side. So what theta would that be? All right, that should be a theta of pi. So we're going from 0 to pi. That's our limits. Okay, so I'm gonna put 0 to pi here. 0 pi. That's my limits, and then same thing for the other term, integral 0 to pi, and this would be cosine theta d theta I hat. Okay, so pretty simple integration, right? Cosine integral of cosine theta, integral of sine theta. We know how to do those. Now, integral of cosine theta, which I believe gives you, what would that be? Oh, that's good. My memory's telling me negative sign. It doesn't really matter whether it's negative or positive, because either way you get sine, right? Sine of pi, sine of 0, right? Looking at those limits, that's going to give you 0, right? So that whole integral right here goes to 0. All right, which makes sense because we said that we shouldn't have an x component and it should cancel out, and that's exactly what we see there. That integral cosine theta with those limits, 0 to pi, gives you a 0, and then what we're left with on this side, on the other integral, or integral sine theta, I believe that gives you a negative cosine theta, which then, when you plug in those limits, gives you 2. So here's our equation, our final answer. Oops. Force equals 2I RB, J hat. Don't forget about that J hat. There we go. Okay, so that's how we do it. We had to go back to looking at a small segment, but once we consider that small segment, you know, we've defined our DL, and I think that was a critical point in this. If you don't define your DL, doing the rest of this is going to be really tricky. So we had to define the DL in terms of this angle, and then once we did that, it's just plugging in, and all this here was algebra and a little bit of calculus at the end. So I don't think it was too tricky. All right, so we'll take a break now. We'll come back. We'll start looking at torque acting on wires.